Coming back, our next speaker today is Laura Caune from Riverlane. And over to you, Laura. Thank you.
Yeah. Hi. So as already stated, my name's Laura. I'm a quantum scientist at Riverlane. And yeah, thank you for the organizers for inviting me. I'm definitely very happy to be here. And I'll be talking about Riverlane's work on demonstrating real-time and low-latency quantum error correction with superconducting qubits. And this is really fun for me to talk about because this was really sort of combining a bunch of different things that Riverlane works on. So the gist of this project was to take our hardware decoder and integrate it into a quantum computer's control stack. And so this then became a collaboration between the Riverlane and the Rigetti teams, where Rigetti provided the quantum computer and its control system, while Riverlane built the hardware decoder that was then integrated into Rigetti's control system. So to talk about this project, I'll first talk about quantum error correction and real-time decoding to hopefully give a motivation of why we wanted to do real-time and low-latency quantum error correction. Then the decoder that we built itself is an FPGA decoder, so I'll talk about it a bit more in detail. Then I'll talk about the work we did on integrating the FPGA decoder into Rigetti's control system. I'll then talk about a stability experiment, which is the quantum error correction experiment that we ran to be able to test our decoder process. I'll briefly talk about Anka 2, which is the quantum computer that we used. And then finally, I'll give the results. So the first bit is probably very familiar to everybody already, but let's give it another go. So as you all know, quantum computers are noisy, and various quantum algorithms that offer advantage over classical algorithms are going to require hundreds of qubits and billions of operations, all of which are noisy. So to tackle the noise in the device and unlock such quantum algorithms, we are going to need quantum error correction. So in quantum error correction schemes, we take many physical qubits, and we encode a logical qubit, and that way we protect the information. So here I've shown the surface code, which is one of the most widely researched and promising codes that we currently have. And so here then, the yellow points correspond to data qubits, which are used to store information. The black points correspond to ancilla qubits, which are used to measure stabilizers, which are these operators shown using the colored areas. And on a surface code, Z and X logical operators can be just represented as these chains of operators connecting opposite boundaries. So I said that the ancilla qubits measure stabilizers. And so the stabilizer measurement outcome is flipped from the expected one, or we could say lights up, if an error happens that anti-commutes with a stabilizer. So suppose you have a Z error on a data qubit, then the Z error would anti-commute with the two neighboring red X stabilizers. So if you were to measure them, these would flip. Now, of course, we don't know the locations of the errors ahead of time. This is exactly what we want to compute. So to do this, we can take the stabilizer measurements, which we call a syndrome, and pass it to a classical algorithm known as a decoder, whose task is then to find the effect of the most likely error consistent with the syndrome. So for example, suppose our syndrome looks like shown here with the red points. So the red points correspond to the stabilizer measurement outcomes that have been flipped. Then this could be explained by a Z error and an X error, where the X error has flipped the Z logical. So a decoder is then successful if the correction that it computes has the same effect on the logical as the error that actually happened. Now, of course, we can also have errors on ancilla qubits. So to be able to detect these, we need to repeatedly measure out stabilizers. So our decoding problem actually becomes a three-dimensional graph with the time running up as shown here. And now each edge here then corresponds to a possible error location. So here now then, the horizontal edges would correspond to data qubit errors. The vertical edges would correspond to measurement errors. And these diagonal or hook errors correspond to errors during syndrome extraction circuit. Now, the syndrome then itself manifests on the decoding graph as some nodes sliding up. And the task of the decoder is to pair these nodes using minimum weight edges. But now, it's important to understand why this decoding needs to happen in real time while the stabilizers are being measured. So to think about this, let's first consider Clifford circuits. So here then, in these circuits, each line actually represents a logical qubit, which could be a surface code patch consisting of multiple physical qubits. So now, as long as we can detect where the errors happened, in Clifford circuits, we can just commute the errors through the Clifford operators to the end of the circuit and then just reinterpret the measurements. So this means as long as we can store the stabilizer measurements, we can just decode in post-processing, figure out the error locations, commute it to the end of your circuit, and then just reinterpret your measurement outcomes to obtain the error-corrected result. So this means that with Clifford circuits, actually decoding in post-processing is completely sufficient. You don't necessarily need real-time decoding. However, Clifford circuits alone are not enough because these can be simulated using classical computers, so they don't offer us any quantum advantage. So we will need non-Clifford circuits. But quantum error correction codes alone cannot implement a universal and transversal gate set. So this means we're going to need some logical branching, by which I mean a logical operation conditional on a corrected observable. So for example, here I've shown one of the leading proposals for implementing a logical T-gate on a surface code. And you can see this involves magic state preparation and injection, but then you also have this logical S-gate conditional on a second logical qubit measurement outcome. So that means that now here, at this green point, you will need the error-corrected measurement outcome, so you can correctly decide whether to apply the S-gate or not. So that means then, if you need the error-corrected result here, this is also where you're going to need the decoder result. So now, this means we need live decoder feedback, and now real-time decoding becomes necessary. And because decoding happens during circuit execution, this then will place constraints on the decoding problem, in particular, how fast the decoding problem needs to be solved. So one such time constraint is due to the backlog problem, which happens when the rate at which the decoder processes data, which we call throughput, is actually slower than the rate at which the data to be decoded is generated. So you can imagine, suppose here in this green bit, you need to do some decoding. But if the decoder is too slow, the second logical qubit is just going to sit there, idle, and acquire more and more data. So it acquires this additional backlog of data, which means that then on the next decoding iteration, you now not only need to decode the data from your quantum computation, but also that additional backlog of data from the previous decoding iteration. So now you end up with even more data to decode. So your decoding process is going to take even longer, which means the second logical qubit is going to be sitting there and idling even longer, acquiring even more of a backlog of data, which means in the next decoder iteration, you now have even more data to decode. And again, the decoding process is going to take even longer. So you can see how in this way, if your decoder is not fast enough, you essentially end up with this ever-growing backlog of data on each decoder iteration, which then can exponentially slow down quantum computation. So let's think about what happens in practice if your decoder is too slow. So on superconducting devices, a single round of QEC can be generated as fast as in 1 microsecond. But for simulating chemical elements such as FOMOCO, we're going to need in the order of 10 to the power 10 gates, which means that on a full-tone quantum computer, even with no additional lag, this simulation is going to take a few days. Now, suppose the decoder is lagging just a tiny bit, and suppose it's on average 1% slower than the rate at which the data is generated, then now the simulation is going to take much, much longer than the age of the universe. So you can see how if your decoder is not fast enough, like any quantum advantage we have is instantly killed. So this means that we want to avoid the backlog problem by having our throughput to be faster than the rate at which data is generated. So this means you will either need a very fast decoder, Or you can have a slower decoder, but you can parallelize decoding over multiple decoder threads so that you're still processing a large amount of data in a shorter amount of time. Now, a second key parameter to optimize is the full decoding response time, by which I mean the time between the final data extraction and applying the logical conditional gate. So now, this includes both your full decoding time, but also any additional control and communication latencies in your system to, for example, send the measurement to the decoder and send the decoder result to the control stack. So you see now how then for logical operations that have logical branching, this full decoding response time sort of becomes a direct part of it. So the full decoding response time can be a speed bottleneck for such logical operations. So then the full decoding response time is also going to affect your logical clock rate and how fast you can execute fault-tolerant quantum algorithms. For example, Craig Gidney et al. From Google assumed 10 microsecond full decoding response time to show that 2048-bit RSA integers can be factored in 8 hours using 20 million noisy superconducting qubits. Now, based on a back-of-the-envelope calculation, if this full decoding response time was instead 100 microseconds, then now this algorithm would take more than 6 times slower, likely even more, because the longer your full decoding response time, the larger code distances you're going to need, and this will further slow you down. So this means that we need real-time decoding, and to obtain these fast full decoding response times, we really need to minimize the control and communication latencies in our system while keeping decoding very fast. So with this, keeping in mind this minimizing the latencies, this was kind of what motivated Riverlane to want to integrate the decoder tightly into a control system. So now, just to summarize, I've talked about 2 separate different things. So there's the throughput, which is defined as the decoding time per QEC round. And this needs to be faster than the rate at which data is generated, so you don't end up with the backlog problem, which then can cause exponential slowdown of quantum computation. And on superconducting devices, this single round of QEC can be as fast as 1 microsecond. Now, the full decoding response time included both the decoding time and also any additional control and communication latencies. And this is going to affect your logical clock rate and the speed at which you can execute fault-tolerant algorithms. So this throughput and low latencies is what motivated us to work with Rigetti and integrate our hardware decoder into their control stack. Now, in particular, the hardware decoder that Riverlane built is an FPGA decoder. So this is what I'm going to talk about next. So I keep using the phrase hardware decoding. So I thought maybe it's useful to do a bit of a comparison of what we mean by hardware implementation versus software implementation. So in software, programming happens using software code. So this is something most of us are very familiar with. So you code in Python or C++. And now the tasks are carried out by software running on a general purpose CPU. And of course, you can update your code at any time by just changing a couple of lines, and now you can run a brand new function, so you can be quite flexible. Now in hardware, programming happens at the level of elementary logic gates, such as AND or NOT. So you chain these Boolean gates together to form your logic, so you have physical voltage running through your system, and that way implementing your function. So now, the tasks are carried out by the physical hardware components themselves. This also means that whatever function we want to run needs to be specifically designed and fixed at the hardware level. So we are less flexible than software. So why even bother with hardware then? So yes, software is cheaper to develop, it's more flexible. But in hardware is very efficient and makes it easy to parallelize tasks. So specifically for decoding, to have this very high throughput and be able to process the data very fast, we will need this parallelism, and this is what hardware offers. Hardware is also deterministic, which makes it easier to schedule the operations in your circuit. Hardware is also more energy efficient, which will become important as we scale. And finally, hardware also has much lower inherent latencies than software. So even if you were to tightly integrate a CPU in a control stack, this will still have inherent latencies due to memory management, operating systems, and cache. So hardware will have much lower latencies. So yeah, as I said, in particular, the hardware that we went with was an FPGA, which stands for Field Programmable Gate Arrays. So I'll try to briefly explain what these are. So the key to FPGAs is that they use these lookup tables, which we can just call LUTs. And essentially, rather than computing a function in real time, in a lookup table, you can pre-compute ahead of time all the outputs of your function given some variable inputs. And you can just store them in a lookup table, which means that rather than processing the function in real time, you can just look up the answer in your lookup table. And this is much, much faster than doing the function in real time. So then an FPGA consists of a bunch of these lookup tables, where each lookup table is responsible for some smaller Boolean logic. And these lookup tables can be chained together. So an output of one lookup table could be an input to another. And this way, we can implement more complex circuits. So because these FPGAs consist of the lookup tables, which, you're not processing the function, you're just looking up the output, this means that they're very, very fast. FPGAs are also more flexible than other hardware because you can just reprogram the lookup tables to do something else and that way implement a new function. And also FPGAs are very beneficial if your tasks can benefit from being parallelized. So for decoding, FPGAs will be very useful. Now, the decoder algorithm that we implemented on the FPGA is, we call this a collision clustering decoder. And this belongs to the clustering decoding algorithm families. So I'll try to briefly talk about those now. So in clustering decoding algorithm families, you have your syndrome. And you first try to partition your nodes in the decoding graph into these neutral clusters, where by neutral, we mean a cluster on which the decoding problem can be solved locally. For surface code, this means a neutral cluster is one that either touches the boundary or has even parity. And then once you have partitioned your syndrome into these clusters, you can just solve the decoding problem locally on them separately, and any correction in a cluster is equivalent. Our collision clustering algorithm is closely related to union find by Delfosse and Nickerson. So I think it might be useful to just briefly sketch out what it does. So here I've represented the decoding problem in 2 dimensions, just to make it a bit easier to think about. So you start with your initial syndrome, and each node, each vertex is initially actually a cluster in itself. And then, in order to get to these partitions, you do these growth steps. So say here in this first step, you grow in each direction by half a step. And you see that you have these 2 clusters that have formed, and both of them have even parities. So you can just designate these as neutral and stop growing them. Then on the next step, now this cluster is touching the boundary. So now it's also become neutral. So you can designate as neutral, stop growing this one. Then you do another growth step. Now this bigger cluster has continued growing, and it has merged with this cluster that previously was neutral. But now this neutral cluster, not neutral anymore. It's joined this bigger one, and it keeps growing. And then finally, on the last step, you have grown these 2 neutral clusters. You've done your partition. And then we just run a peeling decoder that solves the decoding problem on both these clusters independently. Now, Das et al. Proposed a union find architecture implementation in hardware. And in particular, for this growth step, they suggested using spanning tree memory, or STMs. And essentially what this is you can think of it as an array where you have a bit for each node and each edge that you can grow. But this means that during union find, you're going to be doing a lot of read and write instructions And this can be a potential speed bottleneck because a single read or write can take as long as a single clock cycle. So this raised questions at Riverlane: can we be more efficient? And this is sort of what prompted the collision clustering decoder. So now in collision clustering decoder, the idea is that instead we use a table. So again, we start with our initial syndrome configuration. Now each vertex is initially its own cluster. We label all the vertices, we record them in a table, and we also record the coordinates of each vertex in your decoding graph. Now, how do we grow the clusters? Well, we just record the radii by which they have grown. So because initially we only grow by half a step, in the table now, each cluster has a radii of 0.5. So you can see now how this only requires 6 writes rather than the 24 that were required for an SDM. Now, we've grown the clusters. How do we know if they've collided? Well, what we can do is we can compute the distance between each pair of vertices and compare that to the sum of their radii. And then this way we can see whether they've collided or not. The good thing about this is that computing the distance is very efficient. This is just simple arithmetic that's very cheap on hardware. It's just a few clock cycles. The not so good thing about this is that now you need to do a comparison between all pairs of vertices. So this collision checking can take up to the size of your syndrome squared over 2. Now, we can also sort the collision record using trees, and that way we can keep track of these neutral clusters and what our clusters look like. And you can then see how, in this way, we can continue growing the radii until we have achieved this neutral partition. And then we also don't actually have to run the peeling decoder because we keep track of the effect of each cluster on the logical during the growth stages. So yeah, this was a little aside on what the actual algorithm is. So then the FPGA was an implementation of this collision clustering decoder. This implementation worked on a surface code and a repetition code, and it can decode up to 1,000 qubits. The FPGA has multiple decoder core engines where each core can support a different decoder type or size. And we can also do live collection of performance metrics. The FPGA was also optimized for running at high clock frequencies, and it can coexist with other system and logic on the same FPGA fabric. Yeah?
Sorry if this is already covered. Do you have to reprogram your FPGA if you want to grow the distance of your code, for example? Or?
Yes. So we had already decided, I can't remember exactly, I think that we can go up to 25 measurement rounds. Oh, the question was, do you need to reprogram the FPGA every time you want to do like a different code size? So the FPGA itself could support, I think, up to 27 measurement rounds. So yeah, before each experiment, we need to send it the configuration, and it kind of sets up the decoder. But we couldn't go to more than 27 because it's fixed. Yeah. But Riverlane is working on a more flexible decoder now because, yeah, we encountered a lot of problems with the fact that it's quite fixed. Yes, Timo?
So your radius search, does it work only for uniform edge weights, or does it also work for non-uniform edge weights?
I believe it should work with non-uniform as well, but in our implementation, we didn't have weights. So it was very simple. Yeah, this was the first time we tried doing this, so we kept it simple. Yeah? I wish I could. I am unfortunately not a hardware person, so I can't talk much more. Yeah, sorry. I can direct you to some of my colleagues who did the implementation. Yeah.
I just have one more other question. So you're saying that these FPGAs are pretty easily reprogrammable. So if you had errors that changed over time, how easy or hard would it be to change your endpoints?
So the kind of difference, for example, with an ASIC is that in an ASIC, you design exactly what your hardware is going to be, and then it's very expensive to make. You get your chip, and this is it. This is all you can do. In an FPGA, you can reprogram what exactly these lookup tables do, so you can have like a new function. But still, it's obviously not going to be as quick and easy as in software, because especially working with a second party, we need to do a full new release, a full new thing. So we did encounter this problem that, for example, later down the line, we wanted the decoder to be able to support reset gates. But because, yeah, this release takes a while, we just couldn't do that. Yeah, I hope that answers it. Cool. OK. There's also another paper by Riverlane where they talk about the FPGA decoder in much more detail, so maybe even the parallelizing question, maybe it's answered in this paper. I don't know off the top of my head. They also did lots of simulations, and they showed that the FPGA has been validated to be able to operate a 400 megahertz clock frequency, so it can go quite fast. They also showed that for surface code memory experiment distance 21, this FPGA implementation uses only 5% resources of a $1,000 FPGA. Again, I'm not a hardware person, so I didn't know if I should be impressed by this or not, but then my colleagues explained to me that apparently normally FPGAs that are used to have them be big enough and powerful enough, it's more like $70,000. So this is very efficient and doesn't take up a lot of room. Yeah, did you have a question?
Yeah, is this for multiple rounds of like simpler measurement and extraction?
Yes.
How many?
I'll cover it in the results, so then I'll talk about how many we did. So this is for memory experiment on a surface code. Yeah, so you just increase the distance. I think you just do one round. No, it's decoding time per round, so I don't know exactly how many rounds they did. Yeah. They also showed that for a surface code memory experiment up to distance 21 with physical error rate of 10 to the minus 3, this FPGA decoder can decode within the 1 microsecond threshold for a superconducting device to beat the backlog problem. OK, so Riverlane did a lot of work on this FPGA decoder. Then we started talking to the Getty, and we came up with this idea that why don't we integrate the decoder into their control system. And this was really very joint work and a lot of effort from both companies. So I'll briefly talk about that next. So just briefly, the Getty's device in particular that we worked with was the Anka 2 device, which is a superconducting device consisting of 84 qubits. And it's got this square lattice connectivity, which makes it suitable for surface code experiments. So of course, the decoder wants to receive the measurement outcomes. And in the Getty's control system, each qubit actually has 6 sequencers for control. And the classified readout results are automatically broadcast to all of these sequencers via this low latency results crossbar. So this means the decoder needs to get the measurements, but all the sequencers will receive the measurements. So this meant there was quite a lot of flexibility where exactly to integrate the decoder with in the control system. And in the end, the Getty team opted to integrate the FPGA decoder with one of their gate sequencers. So basically, rather than Riverlane giving them a physical FPGA, their control system consists of these FPGAs, and a gate sequencer sits on a specific FPGA. So Riverlane gave the Getty the IP, the code for implementing this FPGA function, so they would just integrate and put that on their already existing FPGAs in their control system. So once the decoder was integrated, we could use the processor's existing input-output port interfaces to access the decoder core registers and be able to read and write to them. We also used existing and wrote our own custom assembly language level instructions to be able to communicate between the decoder and the rest of the control system. So in the end, we essentially ended up with sort of like a prototype compiler that can take in your PyQuil circuit and just insert the instructions to be able to interact with the decoder. So this is kind of roughly what the compilation pipeline looked like in the end. So we start with our native gate set and the experiment definition. Then based on that, we would obtain the circuit description in STIM. Then we take the specific QPU's configuration and transpile the STIM circuit to a PyQuil-based circuit, where PyQuil is the native language for the Getty. In the meantime, the stim circuit could be combined with a noise model to also obtain an offline decoder and be able to decode offline as well. And also based on the specific decoder configuration, that's when we would create these decoder sequencer instructions, which are then inserted into this base PyCool circuit. So they essentially end up with this full circuit that has all the decoder instructions in them as well. And then the circuit can be just run via cloud service. So essentially, you have your circuits, all the gates get executed automatically, and the measurements get automatically sent to the decoder. It starts decoding when it's received the allocated number of measurements, and then it can also automatically output its correction through the control stack and execute a second conditional program based on the decoder result. Okay, so this was all about the sort of engineering work of integrating the FPGA decoder in the control system. But then, of course, we wanted to run some quantum error correction experiments and see how the decoder performs. So in particular, we run a stability experiment, which I will now describe. So you can think of the stability experiment as the jewel of the perhaps more familiar memory experiment. So while in a memory experiment, you are protecting your logical in time, so you know what logical state your logical qubit is, and you just want to keep it in that state across time. So then for memory, the distance is determined by the code size. And for memory, logical error actually increases as you increase your number of measurement rounds. Now, the stability experiment is like the jewel of this. So in stability, you want to test your ability to protect your logical across space. So what this boils down to is you essentially have a known product of stabilizers, and you want to see whether you're able to correctly measure out this product of stabilizers. So then here now, the distance is determined by the number of rounds. And the key to a successful stability experiment, this is something that is very important, is that now you increase your number of rounds to show logical probability suppression. So for memory, you increase the code size. For stability, you increase the number of rounds to see logical probability suppression. A nice thing about stability is that you can actually run it on a very few number of physical qubits. So here I'm showing a 2x2 stability on 9 physical qubits. So you see we've got these data qubits labeled 1, 2, 3, 4. Now, you can see there's exactly 2 Z stabilizers associated with each data qubit. So if you were to take the product of all the Z stabilizers, this is actually just the identity. So you know that if you were to measure out these boundary Z stabilizers, and if you had no errors in your system, you should necessarily measure out +1. So this allows us now to test our decoder. So what we do is we measure these boundary stabilizers multiple times. We pick one of the rounds as your logical, where we see, did we measure out +1, or was there actually a logical error and we measured -1? And then we compare that with, was the decoder able to correctly detect a logical error? Now, there's 2 types of stabilizers involved in a stability experiment. In our work, we actually did something we call a stability 8, where we did not measure the middle X stabilizer. This, of course, made the circuit simpler so we could achieve better results. But of course, in real practical photon quantum computation, you are going to need to measure out both types of stabilizers. So this was really a simplification. On the right, I've shown the circuit to measure the Z stabilizers. And as you can see, this includes single qubit rotations, CZs, and measure gates, but we did not have reset gates available. So then, why even care about stability at all? Well, stability tests your ability to correctly measure out products of stabilizers. And this measuring out products of stabilizers is going to be a key step in logical operations such as lattice surgery or moving a logical qubit, or for feedback from the stability-like sections. It's going to become key for performing teleportation. So if in any of these operations you incorrectly measure out the stabilizer product, you will end up with a logical error, which is, of course, something we want to minimize. So this is why stability is important. And we can so then use the stability experiment to determine how many rounds of measurements are needed for logical operations so that you can be confident in the stabilizer measurement outcome. So this was stability. Now, of course, another important key component in this work was the actual quantum computer. So the Getty gave us access to their Anka 2 device. So I will try to briefly talk about it. So Anka 2, as I already said, is a tunable coupler superconducting device with 84 qubits on 7 columns and 12 rows. And it's got this square grid connectivity, which makes it suitable for performing surface code experiments. Now, when we started working with the Getty, they already had built Anka 2. And the Anka 2 Hamiltonian circuit was actually optimized for iSwap gates. But the decoder we built was already with CZs in mind. So what the Getty did was they picked 9-qubit sublattice on which they enabled these CZ gate interactions. But yeah, the device was really optimized for iSwaps, so this was a bit of a challenge to make these CZ gates good. They did some error budgeting, and the Getty found that almost 50% of the CZ error are due to the T-phi or phase errors, almost 25% are due to T1 or relaxation errors, and about 20% of CZ error was due to the higher state leakage. Now, a point of pain for us during running these experiments was actually the leakage to second excited state during mid-circuit measurements. So again, when we started working with the Getty's Anka 2 device, it was already a calibrated, ready-made device. But what we noticed was that because the measurements originally on the device were optimized for end-of-circuit readout fidelity, this meant that during mid-circuit, leakage was really accumulating and really hurting our results. So to try to lower the leakage in the device, the Getty came up with this experiment. They ran this experiment where basically they first excite the qubit to the first excited state. Then they apply this test readout pulse with varying amplitude. Then after a sufficiently long delay to let the resonator depopulate, they would apply a final measurement optimized for 3-state classification. So this way, they could now measure for, as they vary the readout amplitude, what is the probability of the qubit remaining in the classified state after measurement. And they found that this actually looks almost like a step function. So just below 20, you can imagine there's almost like a threshold. That if your amplitude is lower than this threshold, then you're better preserving the qubit. But if you go above this threshold, then now the population is moving much more evenly between the 3 states. And yeah, of course, for us, the leakage, minimizing it was very important and hurtful, especially because we did not have reset gates available. So after running these experiments, the Getty team lowered the amplitude for mid-circuit readout in an effort to reduce leakage. They also shortened the duration of readouts since this was more beneficial for quantum error correction. And they also optimized ancilla qubit readout pulse parameters for maximum fidelity when these measurements are performed in parallel. So yeah, the Getty team really did a lot of work to try to make their device as suitable for QEC as possible. Also, we can't really do a direct comparison with other devices because their device is this vertical I/O, which will be important for when scaling. But yeah, it makes some things slightly harder. And so what we were left with in the end was a median measurement fidelity of 93%, a CZ median fidelity of 97%, and a single round of QEC on this particular device with no resets was about 1.7 microseconds. So now, before moving on to the final results, I thought I'd do a quick recap of everything I've talked about. So I introduced the Riverlane's FPGA decoder, which was then integrated into the Getty's control system. And in the meanwhile, we also did a lot of work together with the Getty to run the stability experiments and other experiments to try to get the Anka 2 to be as suitable for QEC as possible. So finally with that, I will present our results. So again, we ran stability A experiment, decoded in real time, using our FPGA decoder, integrated into the control system. Now remember earlier I said the key to a successful experiment is, successful stability experiment, is that you should see logical probability suppression as the number of measurement rounds is increased. And so here in dark green, we plot the results with the FPGA decoder, and we see that for this experiment, to get these physical error rates were low enough to show error suppression as the number of decoding rounds is increased. We also decoded offline, and we saw that FPGA decoder performance for this experiment is comparable to minimum weight perfect matching or belief matching. But without having resets, the best we obtained was when decoding offline with minimum weight perfect matching, using soft info and pairwise correlation method. Then we got to about 17% at 25 decoding rounds. And this is because the soft information and pairwise correlation methods gives the decoder more detailed information, so this decoder can be more accurate. So yeah, in future iterations of our decoders, we are looking to update them to be more sophisticated as well. Yeah.
Sorry, what are you referring to with the pairwise correlation method? You only check it for one type of check, right?
Yeah, so I mean like when you get the decoding graph, you update the weights based on like actual experiments that you have run.
Yeah.
Yeah.
I see, so that's okay.
Yeah, that's what I mean by
So
pairwise correlation.
correlated decoding and
No, it's not correlated. No, yeah, sorry. I appreciate how that name might be confusing. Right, you might also notice that the data points fluctuate in time. This is because, for each decoder, we need to have a specific configuration. So you can't just kind of take subsets of data and then decode. So actually, each data point here corresponds to separate runs on the QPU. And it is known that the QPU performance fluctuates in time, and so our data points fluctuate as well. Now, I kept saying that we did not have reset gates available, but during this project, we did obviously think, what else can we do to maybe improve the logical probabilities? So what we did was we sort of did a very rough first initial calibration implementation of reset gates that was not optimized at all, but we were just curious what's going to happen. So the hardware decoder could not support reset gates at this point, so we decoded this offline. And we did see that if we had reset gates available, you can gain about 1–2% improvement in logical probability. So in the future, we'd look to use reset gates. Now, before I talk about the timing results, I'd just like to remind again what I talked about at the beginning. So I introduced the concept of this throughput, which is defined as the decoding time per QEC round. And I said that this needs to be faster than the rate at which data is acquired so that you don't end up with this backlog problem, which then can cause exponential slowdown of quantum computation. And on superconducting devices, a single round of QEC can be as fast as 1 microsecond. So we want to be faster than that. So here on the left, I'm showing the mean decoding time per decoding round as the number of decoding rounds is increased. And we see that up until at least 25 decoding rounds, we are on average below the 1 microsecond threshold. So if we use this as a streaming decoder, we should be able to avoid the backlog problem. Notice there's also an upward slope in the mean decoding time per decoding round as we go to more decoding rounds. And this is mostly due to the fact that when you have more decoding rounds, you are running a deeper circuit. And the longer your circuit, the more errors in it. And the more errors, the slower the decoding. You can also see on the right where we have the decoding rounds versus defect rates, that as we go to more decoding rounds, the defect rates increase, meaning we've got more errors. Here, with the solid lines, we're showing the distribution of the mean decoding time per decoding round. But now, with the crosses, what we did was we took all our experiment shots and we sorted them into 100 nanosecond bins according to the specific shot's decoding time. And then for the experiments within each bin, we computed the average logical error probability, which is what we plot here. And we see that most of the time we are below this 1 microsecond threshold, which corresponds to high likelihood of correctly solving the decoding problem. However, there are instances when we are above the 1 microsecond threshold, and this corresponds to higher logical error probabilities. So this corresponds to shots when we had more errors happen, and so we had more defects, and this meant the decoding process was slower. But the logical error probabilities that these longer decoding times correspond to are not going to be useful for practical photon quantum computation. So the noise in the device will need to be improved, suppressed, and we will need logical error probabilities. So we expect that as the device improves, we should reliably be below the 1 microsecond threshold. And so, if this was a streaming decoder, then the backlog problem should be avoided. Also, I said earlier that the decoder was validated to perform at 400 megahertz frequency, but due to the sequencer that the decoder was integrated with, it was actually run in these experiments at 156 megahertz frequency. We'd also be looking to next time execute a full capacity, so we should be faster. And also, we are updating our decoders to be parallelized, which should further improve throughput. The second parameter that I introduced earlier was this full decoding response time, which was the full decoding time and also any additional control and communication latencies in your system. And this full decoding response time then affects your logical clock rate and the speed at which you can execute fault-tolerant algorithms. So the stability experiment could have actually been decoded offline, but the real advantage of real-time decoding is when you need this fast feedback already in your experiment, and then you start caring about the full decoding response time. So to this end, we designed and ran sort of like a stepping stone experiment to logical conditional gates. So what we did was we ran our stability experiment, then waited for the decoder to finish. Then based on the decoder result, we would apply a conditional physical X gate. So then this allowed us to measure this full decoding response time in our system and also quantify the contributions of the control and communication latencies to this full decoding response time. So here, this plot then shows the full decoding response time as the number of rounds is increased. Here, the full decoding response time is computed using the clock cycles that we stored during computation. So you basically record how many clock cycles each operation takes, and then you can compute how long the whole thing took. So we see that as the number of rounds increases, the decoding time becomes the dominant contributor to full decoding response time. But there is still a significant contribution from the control and communication latencies. In particular, the readout propagation takes about 1.4 microseconds. So you need to wait these 1.4 microseconds before you can even start doing any decoding in the system. The rest of the control system latencies are due to things like repackaging measurements, converting measurements to syndromes, sending measurements to decoder, and sending the decoder result through the control stack. Also here, the black error bars represent the standard deviation of the decoding time. And the orange error bars show the standard deviation for the full decoding response time. And you can see that these actually match for each number of rounds. So this means that there is no variation in control and communication latencies for a specific number of rounds, which is, of course, something we'd expect and like to see. We also wanted to make sure that there are no additional operations that would be a significant contribution to the full decoding response time that maybe we forgot to account for. So in order to do this, we also measured the full decoding response time using qubits T1 time. So essentially, because in our circuit we measure out all the qubits, then we do this conditional X gate, and then we measure out again. We could use the qubits T1 time to figure out what is the delay experienced by the qubit at the end of the circuit. And then based on this, this way we could also compute how long this control and communication latencies plus the decoding time, so how long was this full decoding response time. And then we plot this with the blue markers, and we can see that this closely matches the full decoding response time that we computed using the control clock cycles that were registered. So with this, we can conclude there were no additional significant latencies in the system. So finally, what we obtained was that for nine rounds, we end up with a full decoding response time of 9.6 microseconds, where 6.5 microseconds are due to the decoding time and 3.1 microseconds are due to the control and communication latencies. So we were able to achieve these low latencies because the decoder is sitting tightly integrated into the control system stack. So that's why everything could be so fast. But of course, it's going to be very important to be able to maintain this fast full decoding response time as we scale and go to larger experiments. So then this brings me to next steps. The logical probabilities that we achieved are not going to be low enough for practical photon quantum computation. So work needs to be done to improve the noise in the device. So for this, we could further fine-tune the readout pulses to be faster and higher fidelity. If resets aren't available, better tune the readout pulses to better preserve the classified state of the qubits. We also saw practically that resets should help, so making resets available would be great. And also just continued work on CZ fidelities and longer T1 and T2 times should help. As for the FPGA decoder, as we scale and go to larger scale experiments, we are updating this to be a streaming decoder, and we're parallelizing decoding so that we can maintain this high throughput and avoid the backlog problem even with bigger experiments. We'd also look to execute a maximum frequency next time. And to improve the accuracy of the FPGA decoder, we would look to enable weights to the decoding graph and also enable updates to the decoding graph in real time, so we can do things like soft information decoding, leakage-aware decoding, and correlated decoding. There's also steps we can take to further reduce the latency in the system. So I said this readout propagation currently took 1.4 microseconds. But this could be lowered by having a more direct line of communication between the readout sequencer and the decoder stack. And also, there's functionality that's repeated that we know takes a while. So for example, every time we're repackaging the measurements, in this system took 400 nanoseconds. So such repeated functionality could be offloaded to custom hardware logic attached to the decoder, which would also speed up the latencies. So to summarize, together with Rigetti, Riverlane integrated an FPGA decoder into their Anka 2 control stack, and we run real-time decoded stability A experiments using this FPGA decoder. And we showed that logical errors were suppressed for a stability A experiment with increasing number of decoding rounds. We showed mean decoding times per round under the 1 microsecond threshold, which means if this was a streaming decoder, we should be able to avoid the backlog problem. And we demonstrated low latency full decoding response time of 9.6 microseconds with a total of 9 decoding rounds for an 8-qubit experiment. So the fact that our decoding system should be able to avoid the backlog problem and has this low latency full decoding response time means that as the device improves, we should be able to demonstrate logical branching experiments, which will be an important step towards universal fault-tolerant gate set. So with that, I thank you for listening.
Thanks for a great talk, Laura. Questions?
Thanks for a great talk. So on your guys' clustering algorithm, do you have all the weights on the matching graph just like uniform?
Yeah, we don't use weights in the hardware decoder. Yeah.
That would increase the time complexity of like decoding if you allow for different weights.
I don't think necessarily. I don't know about FPGA, how that would work, but the kind of next decoder that Riverlane is building will have weights, and we haven't necessarily seen that it would hurt us. Yeah. Yeah.
You said within the clusters you use appealing.
Mm-hmm.
What is that, sorry?
I'm not an expert in the clustering decoders, so this was just me trying to summarize what the team did, so I can't explain. But I think, yeah, there's maybe other people in the crowd who worked on these before who can explain. Yeah. Yeah.
Caune?
Yeah, you have this very nice data on the distribution
Yeah.
of the runtimes, and the mean is below this threshold you're looking at. Can you say something about how you plan on handling longer runtimes in a real-time situation?
Yeah, so this was not parallelized, so that's absolutely the first thing we want to do. Parallelize decoding so that the throughput can be higher. Our decoding is already really fast, so I think, yeah, if you were to parallelize, this would really help. Again, yeah, we did not execute at maximum frequency, so our FPGA decoder is capable of being much faster, so that's something we'd look to do. But yeah, really the main things is parallelize and stream decoding. Yeah.
So you're saying sort of bring the whole thing down so even the slowest time is faster?
Well, you also only care about the average time. So you can still have some instances when you're about the 1 microsecond. You just need to be on average faster. And yeah, also as the device improves, you're going to have less errors, and then decoding also should be faster. Because yeah, these 40, 50% logical error probabilities are probably not going to be very useful. Yeah. Yeah.
From the nice one. I'm wondering how portable is this entire scheme? Because you've done this integration with Getty. If I come along with a new hardware, perhaps also a control device as an FPGA, would you be able to just use this again, or there's a lot of customization?
Yeah, I feel like Riverlane's product team would be very happy that you asked this question. So this is kind of what Riverlane's working on now, is building this decoder stack where the whole idea is that now you can work with various hardware partners and they can just plug in the whole decoding stack, and we kind of take care of repackaging the measurements, reformatting them, and then running the decoder. But there might be some slight differences exactly what decoder we do for different types of qubits. But yeah, we are integrating these decoders with hardware partners. Yeah.
I guess, in your opinion, what do you think is the biggest worry or like bottleneck to getting like real-time decoding for like actual algorithms you want to run? Is it with like flexibility with the logical operations and stuff like that, or is it something else?
I think it's really an engineering problem. So you need to figure out the engineering problem. But yeah, also just getting your device there to be able to perform these quantum error correction experiments. Turns out quantum error correction is quite hard. But yeah, I think once the device is there, it's an engineering problem. Yeah. Yeah.
How specialized was the way you implemented the union find to the square lattice? Could you easily adapt it to another graph?
I think so, yeah, because it's just you just have a table and you record, sorry, it's so far away, and you record the coordinates, and really you just do the growing by computing the distance between the coordinates. So if this was a different configuration, I guess it should be fine. But yeah, I was not directly involved in this implementation in hardware, so yeah, I can only briefly comment. I think the paper that we have on FPGA decoder should have much more details.